to understand EDTA titrations, we of course need to understand the equilibria between EDTA and metal ions so that we can understand what's going on with the titration curve, similar to what we've done for precipitation titrations and for acid-base titrations. And to understand that, we need to understand EDTA itself and its equilibrium properties. So as I mentioned in the previous video, EDTA is a hexaprotic acid, which means that it has 6 different places it can lose protons from. And the pKa values for each of these six proton sites in the molecule is known. And so it ranges from pK1 of 0 to pK2, which is 1.5. pK3 is 2.00. These are all pKa values. I'm leaving out the A, but these all represent the acid dissociation constants. All right, then it goes 2.69. And these first 4, these are all the carboxylic acid groups. So these blue groups on the molecule. pK5, now we're getting to the amino groups, and these are significantly higher. And then losing the last proton is the hardest, of course. That's the smallest pKa value, 10.37. And these two correspond to losing protons from this from the amino groups here. Now EDTA is something you can purchase, and when you buy it, it's in a neutral form. So neutral EDTA is often abbreviated as H4Y. So all of the carboxylic acids are protonated, but the amino groups are not. That's the sort of neutral form. So we can range from different forms of EDTA. We can go all the way from H6Y2+. This would be the fully protonated form, to the fully deprotonated form, Y4-. And so Y is just a lot easier to write than EDTA over and over again, so it's a commonly used abbreviation, not to be confused with any elements like yttrium or whatever. So anyway, neutral EDTA is something you can purchase and make solutions out of, and that's what you generally do to do a EDTA titration. And so when we're thinking about what's happening in terms of the equilibrium, we care a lot actually about this version, the fully deprotonated form. And the reason for that is when the metal ions, so we'll just call Mn+, right, whatever metal ion this is, when this reacts with EDTA, the complex that's formed is specifically the metal ion with Y4-. So all the protons get lost because they'd be in the way of the metal ligand bond formation, right? You can see in this structure up here that's behind my face, you can see there's no protons left in here anymore, right? So in these bonds, no H+, right? So all the protons have to get lost in the process of this complex forming. And so we care about the formation of this Y4- form of EDTA. And so this will be N-4. So we define the fraction of EDTA in the different forms. We specifically look at alpha Y4-. So alpha here means the fraction of molecules in the Y4- form. And that's actually defined in this equation right here. So it's just the concentration of Y4- divided by the concentrations of all the other possible forms of EDTA. So H6Y2+ down to Y4-. And a simpler way to abbreviate that is in the equation below, where the concentration of Y4- divided by the total concentration of EDTA. Now, this value is pH dependent. And there's a nice, in your textbook, there's a nice derivation of the pH dependence of this. It's a formula that you can calculate and depends on all the different Ka values for EDTA. We're not going to go through that derivation, and I don't expect you to know how to do that, but it is there. Like, this does come from somewhere. But what we care about is that this is pH dependent and the values are known. There's an equation we can use to calculate the different values of alpha Y4-. So it's from table 12-1 in your textbook. This is it right here. Let me make this a little bit bigger. So the values of alpha Y4 minus for ADTA at a specific ionic strength, we'll just assume that for all the problems we work with, pH 0 up to 14. And what we can see is that there's a huge range here, right? At very high pH, almost everything is in the Y4 minus form, the fully deprotonated form, which makes sense. The more basic the solution, we lose the protons. And when we go to very acidic solution, we get basically nothing that's in the Y4 minus form. So 1.3 times 10 to the minus 23 at pH 0. And so this is relevant for EDTA titrations because those protons need to be lost for the complex to form. And so the value of alpha Y4 minus is going to affect the equilibrium reaction involving our metal ion and EDTA. And so the pH of the titration matters a lot. And so we'll keep exploring that in the next video where we look at some definitions of equilibrium constants between metal ions and EDTA and why alpha Y4 minus matters in those.